This is a BC topic. It is one of the first true BC topics where we're talking about Euler's method. Typically, I show a clip from Hidden Figures where they're calculating the stop-go piece. I wasn't sure about some copyright issues since I have to record my videos and I do post them to YouTube as well in case people in other districts are using them that have asked about my videos. So I do not have a clip from that embedded in here, but please go watch that because they actually reference Euler's and that's how it was used within some of the early moon flights, and it is a pretty cool concept, and you'll see the application there with it. Within Euler's, we're going to have a differential equation, which is capital F of xy. So that is a differential equation. We're going to have our step, and just like our limit for the definition of a derivative, that is really delta x. H is delta x, or your change in x, which we'll call the step. And for a differential equation that's too complex to really integrate, we're going to find the approximation with small steps, which will get us very close to the actual curve of the function, but we will have to have an initial point. So that is our initial point, x naught, y naught. Without an initial point, you cannot do Euler's. To find your x coordinates, you're just going to add the change in x to each point. So from your initial x, you'll just add your step to it, or your change in x to find your next, etc. Y becomes a little more complex because you're going to take your initial y plus the step, so the change in x times the slope, which if you look at this is really y minus y1 equals your slope times x minus x1, where this portion is h. So now we have y minus y1 equals your slope times h, and your slope in this instance is capital F. And then we just add over our y value, but instead of y1, we're going with y naught. So we're just changing that to a 0. So then y equals y naught plus your slope times your step. So it's really just using the tangent line equation modified. So within this, we have our initial plus our step, which is our change in x, times our slope. So it's initial, the change in x, and our slope. And we just continually do that. It's an algorithm. So we'll continually do that each round. We'll add our change in x or our step to our x value, and then we'll calculate our slope from the slope equation, or our y equals mx plus b equation, and just continually calculate a new portion of our values. This is little notebook worthy. Please make sure this is in your little notebook under your differential equations portion. This will be a hot topic for the BC portion of the exam. Now we're going to approximate Euler's method given our information. So we know our step is 0.1, and we know our initial point, so x naught is 0, y naught is 1. And this y prime equaling x minus y, that is our f, or our slope. To calculate the x's, x1 would be equal to x naught plus our step. So 0 plus 0.1 or 0.1. That is our coordinate for our x value. y1 is, now we can calculate. So we have our initial y plus our step 0.1 times our function f. So that is x minus y at our initial x naught, y naught. So that is 0 minus 1. So now we have 1 minus 0.1. And 1 minus 0.1 is our 0.9, meaning our next coordinate pair is 0.1, 0.9. That is the next approximated point for our initial equation given the differential equation or the derivative dy dx for that equation. So we're approximating the original equation's coordinates based off of the slope of that equation in an initial point. So now we need to calculate x2. And I'll change colors. So x2 is x1, so 0.1, plus our step of 0.1. This gives us 0.2. Y sub 2 would be y1, so 0.9, plus our step 0.1 times our differential equation at x1, y1. So now that is x minus y, and our x was 0.1, and our y was 0.9. And this will give us a y2 of 0.82. Therefore, our coordinate would be 0.2 and 0.82 for our second step. For our third step, which is x sub 3, that is our step, our last x plus our step, so 0.3, and our y value for our third step would be our last y value, 0.82, plus our step of 0.1 times our differential equation at our previous points, where x was 0.2 and y was 0.82. This gives us a step 3 of approximately 0.758, and our third step coordinate would be 0.3 and 0.758. I will do one last step. A fourth step would be 0.3 plus 0.1, and that would give us 0.4. Our fourth step for y would be our previous y value, 0.758, plus our step of 0.1 times our previous x minus our previous y. And that comes again from the differential equation that we were initially given. So we're at 0.3, and I didn't leave myself enough room, 0.758. That gives us a fourth step of 0.712. So our fourth step coordinate pair is 0.4 and 0.712. Typically, the AP board will just ask for the y value of a certain step. Other times, they may ask you for each piece. It all depends. Thank you for taking time to watch this video series. This is your homework assignment. I will be posting it online as well. Just make sure that you check it out. Ask questions if you have any from the series. And your assignment will be different than BC or AB's, so make sure that you keep that in mind. I'll be posting one for AB and for BC. Thank you for taking time out of your day to watch this. Let me know if you have any questions. Thank you.